Welcome to the Cosmic Pie Podcast, Episode 2, Season 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota here in beautiful, warm, and... Wait a minute.
Yeah, I was about to say, shouldn't you say Burr from North Dakota?
It's all uphill after this, Robert, in terms of the weather.
And when will Elvis get here?
So we are broadcasting from Grand Forks, North Dakota, where we are feeling winter. We know that, and it makes you healthy and strong. Run through that cold air in the morning, go for a jog. Just don't slip and break your leg.
Yeah, something like that.
We do have a live chat feature that's running, so if you have any comments or questions throughout the podcast, feel free to use that feature. Now, today, Robert, we have a very special guest.
We do.
So today we have Lakma Gamage from New Mexico State University, Alamogordo.
Yeah.
And so, Lakma, we have a direct connection with you, of course. You did your PhD here at the University of North Dakota in the Department of Physics and Astrophysics. In fact, as a disclaimer, and we have a couple to make. Number one, Lakma was my PhD student.
Right.
And the other disclaimer is whatever the three amigos say is our own personal opinion, and not necessarily that of anyone else associated with the university, either UND or New Mexico State University, right, Lakma? You don't want to say something to get you in trouble. So Robert will take full blame for everything.
Oh, yeah. Everybody get the blame for everything else.
Actually, we'll split it between us like a pie.
Okay. A cosmic pie.
You got that? 50-50 slice. How's that?
All right.
So welcome, Lakma.
Yeah, nice to be here. And thank you for the invitation.
I will mention something real quick. If you can't hear Lakmal for any reason, please make that statement, bring that up in the chat. We have had complaints about people not being able to hear our guests. We want to try to correct that, but I've got it corrected as well as I know how to do, to be honest. So, but if it's still a problem, I need to know that. So now, sorry, Lakmal, to interrupt.
Yeah, get nice and close to your microphone, Lakma.
Yep, I'll try my best.
Okay. So you want to maybe give a little bit of intro of your background, where you came from, besides your mother, and other things like that, and then maybe state how you end up in New Mexico.
Yeah, of course. So like Dr. Barkhouse said, I was his PhD student. I started early 2017, I guess. Then I finished my PhD back in 2022. I am from Sri Lanka. I moved to the States for my PhD. Then I got a job offer after I finished my PhD at New Mexico State University, Alamogordo, and I've been here as an assistant professor in physics and astronomy ever since.
Now, Lakma, can you verify that it's actually warmer in Sri Lanka right now than it is here in Grand Forks?
It is. I'll be honest. I was kind of disappointed to see the weather today. It's been in 40s, 50s, but today it's in 30s, even for us. So.
You must be feeling the effect of that cold weather going south.
Yes. Someone just told me it's snowing in Vegas. I'm not sure.
Oh, wow.
Yeah. Oh, it's snowing on the Mississippi Gulf Coast where I'm from. So
somebody said like Florida's expected 5 inches of snow and they don't have any way to deal with it. So it's going to be bedlam probably for a while till it melts away.
Till it melts away.
Wow. I mean, we feel it here. I mean, if you think of Celsius, this morning it was minus 31 Celsius. And that's air temperature without the wind chill. I think wind chill probably in minus 50s.
Right. It was cold.
You put a few extra layers on. You use that new technology. Well, it's not really new, but you use that technology, right? The heated gloves. You need a heated body, an all body wrap, like a mummy.
Right. Need a heated something.
People are complaining here. It's cold, and I'm walking around in a sweatshirt. They're like, really?
Well, Lakma, aren't you the guy that walks around bare feet in the middle of the winter anyways?
Yes, exactly. I walk 2 miles barefoot.
Yeah, Lakma, he had I don't know if he's going to hurt me for saying this, but he had an unfortunate accident where he had to go outside. I think it was in January, wasn't it? It was in the winter. In January in bare feet for a while until he was able to get back into his apartment. So not the pleasant thing that can happen to a person.
Yeah.
I mean, at that point, you feel like stopping by a garbage can and strapping on anything you can find to provide some insulation.
Funny enough, I was actually going to throw out the garbage when I got locked out.
Oh, yeah, that's right. That's how it happened. You put the garbage out and got locked out in the meantime. You couldn't get back in.
And, I've taken it to heart. I've thought about going out and taking my garbage out without bothering to put on real shoes. And I think then about your story, I got to say, and no, we're not doing that.
Yeah, you never ever, at least hopefully, yeah, and there's nobody in your house that can help you open up the yours. Yeah,
Right.
You have to be very
I'm
careful.
just out of luck.
So, Lachlan, whatever got you interested in astronomy in the first place? If I can ask that question, kind of start things off.
So I don't want to say that I've been interested in astronomy ever since. Like I was a kid like you, Dr. Barkhouse, but I was interested in physics mostly. And then when I applied for grad school, obviously I came and talked to every professor at UND. And when I talked to Dr. Barkhouse and Dr. Young, the concept things that came out, and I was very interested, and specifically with what Dr. Barkhouse did. And then, well, next thing you know, you worked together for 5.5 years.
In fact, didn't you do a summer internship at CERN, was it?
Yes, yeah. Summer of 2016, I actually interned at CERN. Then that is what got me interested in grad school in the first place.
Do you want to say a little bit about the instrument? Because maybe some people are listening to this podcast that don't really know what CERN is. You may want to describe a little bit more in detail.
You beat me
So
to it.
CERN is the European Organization for Nuclear Research. In my opinion, if you're a physicist, that's one of the best places you can be at. They have the Giant Hadron Collider, the particle accelerator. Unfortunately, when I was there, I don't think it was operational. It was under construction, but you can go there, intern during summer. You can work for the physics side, or you can work with the IT side. I got chosen to work in the IT side with the IT department at CERN. It's a very neat place. I used to joke around and say I used to sleep in Switzerland and go work in France because I actually had to cross the border to go to my office.
And I'm just going to say that this also brings up a point that I keep trying to emphasize, which is if you get the chance to do these internships, do them.
Yes,
Apply for it, go for it.
I'll be honest. I was like a frog in a well, just like that old saying goes. I was not I don't want to say aware. I was not very keen about getting outside of Sri Lanka and getting out of my comfort zone, go live in another country. But that experience, that 2 months I spent at CERN, it was a major eye opener.
Right.
I came back. All I did was look for grad school, and then I was ready to take the next step.
Yeah, I know here in the United States, there's the NSF-sponsored REU programs, research experience for undergraduate students, as they're called, where students can apply, and there's probably at least a dozen or so every summer,
Right.
where they essentially will pay you money to go to different places, and it could be NASA facilities or elsewhere, observatories, to actually do research with senior people, and also to do other fun activities if there's any type of things going on nearby. So let's go visit different things, museums, planetariums, different telescopes if they're nearby, different experiments in physics. And so I know everybody that I've talked to that have been fortunate enough to get selected, because there is, like several hundred people applying for only 10 positions typically.
Right.
That it turns out that's one of the best experiences they've ever had in their life up to that point.
Which is why even though you're one out of hundreds, you want to take the chance. I mean, we've had Sadie and Parker here talking about their experiences, and now Lockmal about his. You want to take the chance, folks. You really want to get into these programs.
Yeah. I mean, the other thing is almost like the lottery, right? You might say, the chance of winning a lottery is one in so many hundreds of millions, but if you don't buy a ticket, you'll never win. That's guaranteed.
Right.
You just don't have to go off and buy a million tickets, just buy a single ticket to minimize your expense. And that's kind of the
Anyway.
Now, Lockman, the Large Hadron Collider was still under construction, or at least it wasn't operational when you were there?
I believe so. I think maybe they switched it on towards the end of my stay, so it was just 2 months. Unfortunately, I actually had the chance to go under the tunnel, go down to the tunnel and then see it from a distance, not necessarily go stand next to it. But it was an interesting experience. You go 100 meters underground, and then it's all concrete. And then when you come out, they actually give you an active Geiger counter just to make sure Nothing is crazy. So,
Oh well. I mean,
That's
I
really
remember
kinda cool.
that in the year. I think so. The big discovery that was made with the Large Hadron Collider, for those who are not familiar with that, so it's an instrument where you collide protons, right? And out of that collision, energy of the collision can be converted to mass. That's, if you like, the most famous equation of all of physics, equals mc squared, Einstein stuff, right?
Right.
And so out of that, you get new particles conformed. So there's two analogies people make with this. It's like taking two watches, the old mechanical watches, slam them together, and you see wheels and springs flying around. But that's not an accurate analogy. It's like you take two bananas and slam them together, and out comes grapes and blueberries, and so something new comes out of it, out of that
Right.
energy of collision. So what they were looking for was the Higgs boson, the Higgs particle. And if I remember right, the announcement was made, I think, on the 4th of July, 2018. If I'm not mistaken. Wasn't that around that time?
2012, if I'm not mistaken.
Was it 2012?
Yeah,
Yes,
it
it
was
was before I was there. So I was
Oh,
there.
yes. So
Yeah,
what year
And
were
it
you
was-
there?
2016, and it is during summertime because I remember on the day they have pizzas in the cafeteria that actually has the trails or the tracks that a Higgs boson would leave.
That's kind of cool too, in a geeky, weird sort of way.
Okay, so I just looked it up. So the Higgs boson discovery was announced on July the 4th. So at least I had that right.
Right.
I had 2012.
Okay.
So it was discovered before you got there, Lakma.
Yes, it is. Yes.
Okay, so they must have, and I know after so many period of time of running, then they shut it down to upgrade it. So it must have been an upgrade that they were doing when you were there that summer.
Yeah. So they upgrade. I think the energy every time they shut it down and come back up, it's a little higher than what it used to be. So I
Right.
think that's what they were doing.
And
Okay.
I do have a comment on the chat from Bill and Mizuho. They're saying hello, Luckmal. So,
Hi, Dr. Shams.
Okay, so that's interesting. So that's that's still leading, the top envelope in terms of pushing out particle physics technology nowadays is the LHC. There's nothing been built that supersedes that type of energy, and it's going to be a
it's
while
going to be
before
there
that can
for
ever
a while
happen.
too.
Because the higher and higher you go in energy, usually the cost goes with it.
Right. Well, you need a bigger and bigger loop.
Well,
I think they build a 100-kilometer accelerator, if I'm not mistaken. So right now, the accelerator is limited, from what I understand, on one side, Mount Jura, and on the other side, Lake Geneva. So they can expand the current setup. And I believe they're planning to expand it up to 100 kilometers or something like that. So the diameter.
Yeah. And to get into a little of the reason why, not in depth for you folks, so don't freak out, but basically you've got to either have a much stronger magnetic field, which we're pushing the limits of what the technology can do on that score, or you've got to have a bigger circle where you give a smaller magnetic field more time to operate. So
yeah, one of the things, that was the super collider. Remember we talked about this in the past, that they were proposing to the governments in Europe, and I don't think there's been any movement on that issue because of the expense. But the other thing that people are looking at nowadays, if you take two protons and slam them together, protons are messy because they have internal structure.
right.
There's gluons, there's the quarks, and they interact, and they produce a lot of things, a lot of entities come out of that collision. And if you're trying to keep it extremely basic to find, fundamental particles, maybe you want something that's less messy. So there's a lot of junk you got to look through and weed through.
So that you're not seeing the wheels and cogs and springs of the watch. You're seeing the stuff that comes out from the flow of energy.
Yeah, so what they're thinking now is to build a linear collider again, but
Okay.
now have it as electrons.
Okay.
And so you won't reach the same energy, but the thing is, they're much cleaner when you have, let's say, an electron and a positron run into each other, two electrons. There's nothing internal, as far as we know, in those entities. And so they're clean.
Yet.
So basically, you have the energy being converted into particles, right? Rather than,
Which is what we're looking for.
yeah, so there's a lot less type of interactions that would occur, right? There's a lot less of that, strong nuclear reactions that you have to worry about.
Right.
So for an experimentalist, it's a much cleaner experiment.
Right.
And so I think it's a lot cheaper to build than trying to build one of these super colliders that's going to cost, instead of 10 billion euros, it's 100 billion euros. You're just scaling up by an order of magnitude at that point.
Yep.
I
So-
was going to say this earlier. It's interesting that you brought up the research aspect in undergraduate, student life. I'm at a community college, so obviously we don't get to do much research, like at a 4-year school. But we do have a couple of programs. Like if anybody's listening who's at a community college, most of the community colleges have these programs over the summer. You get to go to a 4-year school and then do some research for like a month and a half just to get your foot in the door. And we have one called New Mexico Alliance for Minority Participation. So I'm the coordinator for our campus. I try to find students in STEM field and then try to send them over to the New Mexico State University in Las Cruces or University of New Mexico. So far, it's been very enjoyable process for them.
Excellent.
So it's almost like a feeder system, right? You feed the big school if you can.
Yeah. And
Okay.
very recently, I was approached by someone from, I forgot, mountains somewhere in Colorado. It's called Four Corners Astronomy. So Colorado, Utah, New Mexico, and Arizona coming together to do astronomy specifically for students in rural areas like where I live. And it's all through Zoom. They do basic research. And then hopefully by the end of the semester, they actually can get a publication order too.
Oh, that's
Excellent.
nice.
Yeah.
Nice.
I'm trying to encourage that among students because that's something I always admit anywhere. Without research, I wouldn't be in grad school. Trust me.
Right.
Yeah. Well, the whole COVID business, that kind of pushed all of that, right? People thinking, hey, we don't have to be in the same room.
We can still work together and not be in the same room.
Yeah,
Exactly.
we can just Zoom each other once in a while periodically, right? And have
Mm-hmm.
meetings and so on and still push the research.
Right.
So, in some sense, that's how it's done anyways, right? Like we could talk and have a weekly meeting or whatever, and then I got to go back to my office and think about things that we talked about and to do research.
Yeah.
And I can't sit in front of somebody else who's staring at me, right, trying to think about stuff. Anyways, that's why most of my research is done at night. There's nobody around, right? You need long periods of not being interrupted, right? That's extremely important.
That's important. It is.
Yeah. I mean, I always think about like Kep Thorne, right, who's a very famous, Nobel laureate nowadays, general relativist. So he was a major theorist for the LIGO experiment. He was also, the science person behind the movie Interstellar, if you remember that movie. And he said many times when people interview him, about your life and stuff, what does he do? He works at a Caltech. When he goes to Caltech, he doesn't really do any research. There's always, administration type stuff, service
Right.
type work to do, talking to students, going to meetings, going to colloquia, all these type of things. And if he wants to do like hardcore research, he takes a month or two off and then goes up to Oregon and rents a cabin on the coast and sits there, where there's no distraction at all. In fact, people are not even allowed to call him unless it's an emergency.
Or you take a train ride to a conference and write it out on a napkin while you're in the
Doesn't work
food
too
cart.
often, Robert.
Yeah, well,
We're stuck in a ship like Chandrasekhar.
Yeah, exactly. So, in general, I think most people need a quiet place where they can think.
right. But you do need to get together for meetings
Yeah.
to collaborate. Hey, this is what I've found. This is what I've done.
Yeah, exactly. In fact, when Kep Thorne is away for a month or two, he always have his weekly phone meetings with his students.
Right.
And that was in the past, so I'm sure it's like Zoom meetings now, right? But yeah, you need some quiet time. That's not always provided, where you actually work in the office. Anyways, so Lakma, do you keep up on astronomy as much as possible in terms of the different, research results that come out?
I try to. I'm also the coordinator for the Astronomy League at the Space History Museum up here. And part of my promise to them is keep them up to date on what's happening in astronomy world. So
In other words, you need to keep watching the Cosmic Pie podcast.
yes, exactly. You guys help, and I unfollowed everybody on Instagram, and I'm only following things like James Webb Telescope, European Space Agency, Hubble Space Telescope. So anything that comes up,
Yeah.
I share with them. Yeah.
Yeah.
So
The best. I learn from the best. That's Dr. Barkhouse.
I wouldn't say that, but
No, I'm joking.
We did have somebody commenting that movie,
Interstellar.
Interstellar, was recommended to them. I got to admit, I haven't seen that movie yet.
Oh, it's a very good
I'm
movie.
lagging behind
Matthew McConaughey is into it.
Yeah, I have to surrender some of my Geek Card memberships, for that one, but I haven't seen it yet.
The one thing I like about it is that, sci-fi movies are such that a spaceship goes by and you hear the whoosh, it's like,
Right.
oh, how can that happen? Sound doesn't travel in a vacuum of space. But people demand that whoosh sound, right?
They do.
They're looking for that.
Yep.
Same as things blowing up if you hit them with your lasers and
Right.
photon torpedoes and all this kind of stuff. But the Interstellar movie, the part that I really liked about it is they got the general relativity part of it more or less correct.
Right.
The fact that a planet that orbits a black hole deep in the gravitational well, time for that planet slows down relative to a clock that's much further away from the black hole itself. So
Right.
time dilation effects, and that's where Kep Thorne came in, right? He was the one that
Yep.
pushed for that. And they use that as part of the movie, right? They're on one planet that's close to the black hole, but not too close that it's on
It's
a
ripped
stable
apart.
orbit. But
Part is
time
radiated.
passes, such that you're on the planet for several hours, and yet years go by on a spacecraft that's much further away, orbiting the same black hole.
Right.
So the time dilation was real, at least realistic as much as possible, and that's what made the movie, at least for me, really interesting. So I
Cool.
highly recommend the movie if you have any little inkling of a fan of being the sci-fi type stuff. It's definitely worth watching.
So I'll have to do it.
Yeah, but there's other stuff in it that you can complain
Oh,
about
yeah.
it. But that's want to jazz it up for a Hollywood movie, right?
Right.
There's going to be some liberties that people.
There's some liberties.
the
There's
director.
always liberties taken with a movie.
Yeah, so that is a really good movie. So yeah, so last week, LACMA, the American Astronomical Society, had their biannual meeting. I guess you would say, right? Twice
Is it
a year.
annual
Sorry,
or biannual?
it's not annual. It's every 6 months.
Every 6 months. Okay.
Yeah.
So it's biannual.
Yeah, so
No.
the next one will be in June, I believe. So the January meeting is the big one. It's the one that's I think most attended, and it seems to be usually a lot more news comes out of those meetings in January, and that's the case with this one. And of course, a lot of stuff focuses on spacecraft, right? Because there's so much now. It's like the work done in observatories has kind of been pushed away. You might notice over time now, and everything that's in space dominates. Whether it's the Hubble Space Telescope, whether it's the James Webb Space Telescope, because you don't have to worry about the atmosphere. And that atmosphere, in a sense, provides a large uncertainty on a lot of the stuff that you're looking at
Right.
compared to using space-based telescopes. So, like Elon Musk would say, don't complain about the Starlink satellites going by and ruining your astronomy images. Put your telescopes in space. Then you don't have to worry about it. And there are a lot of advantages of doing that, but of course, the disadvantage is what? Moolah. Money.
Yeah.
It costs money to put your telescope in space, unfortunately. And it's not a little bit of money, it's a lot of money.
It's a lot of money.
I mean, astronomers, if they had endless, if you like, ability to get on a rocket without paying anything, they'd gladly put their telescope in space.
Sign me up.
But it just, you can't afford it. That's the problem. So, LACMA, so I guess we can go to the first slide. Unless,
Okay.
LACMA, you want to say anything?
Oh, we're good. Yeah.
Okay.
Okay.
So the first slide just kind of give people an overview of some of the things that was discussed last week. We had talked about this in the past, the fact that the Gaia mission has officially now ended.
It's ended.
So
It's over.
It is done. So Gaia is a space telescope, essentially, whose job is in the field of astrometry, as we call it.
Right.
And the field of astrometry is the measurement of as good as possible, the precise location of some object in space. So, multiple objects like stars or something. And also to track their motion as well.
Right.
Because we are on the Earth clearly orbits the sun. The sun itself orbits the Milky Way, but so do all the other stars in our galaxy.
But
So-
they're also got their own little motions.
So
within
nothing is
that orbit.
standing still. Everything is moving. And just like when you can look at aircraft, for example, if you see a plane taking off on a runway nearby, you're heading to the airport, it looks like the plane covers a huge angular distance, arc in the sky. And at the same time, maybe if you look way up ahead, here's another plane, at, 35,000 feet, that's traveling much faster, yet it goes much slower across the sky. And that difference, of course, is reflected in the difference in the distance.
Right.
So when stars are really, really far away, it's barely able to notice their motion. And if things are really far away, you can't notice it at all. It's very difficult to see their apparent motion across the sky. So stars that are closer to us, then we see their what's called proper motion a lot better than stars that are much, much further away. And so Gaia was one of these latest, greatest missions that was designed to not only measure the position of stars accurately, but to also determine their proper motion and to watch the stars over time. If you take in observations from different vantage points, you can actually measure through the parallax technique
Right.
the distance of the stars.
Right. Which parallax is, again, just bringing it back up, it's the distance, it's how things shift when you look at it from a different position relative to things that are still farther away. So if you hold your finger out at arm's length and you close one eye and then you open it, close the other, your finger will seem to shift position with respect to the things behind it. That's parallax.
Yeah, and we can extend that to astronomy by just taking measurements of stars, let's say on one side of Earth's orbit in July, and then measuring the same location of the stars, let's say in January. When we're essentially on the other side of our orbit. And that shift in position then will tell us how far away the stars are. But of course, it only works for stars that you can measure that shift. If you can't measure the shift because it's too tiny, you're out of luck.
Right. Which is why we put a spacecraft in space doing that. Gaia.
Right, Lachlan. So what's the advantage then in terms of parallax measurement of having your telescope not on the ground, but actually in space to do these type of observations?
Increase the baseline. The more you increase the baseline, the better you can measure that angle. If I remember right, the parallax to the Alpha Centauri, the closest star, isn't it in like the 10th of arc seconds, if I remember right?
0.77.
That's come up.
Yeah. So,
Less than an arc second, which means it's a little more than 1 parsec away.
Right.
yes. Yeah. So, I mean,
but what do we got to look through though if we're on the Earth?
what do you mean?
Compared to a space-based telescope, what do we got to look through if our telescope is on the Earth? And that could cause us not to be able to measure those small angles.
We got to look through the atmosphere. Like,
Bingo.
That's another disadvantage. So.
That's actually the biggest effect, right? That you can't resolve those small little angles for distant stars because the blurring effect by the Earth's atmosphere.
Right.
So,
If the blurring of the atmosphere makes your star take up 3 pixels on your CCD, and your angle is 1 pixel, you're not seeing that angle.
yeah, so if you have your telescope in space, the best you can do is work at the diffraction limit of the
Right.
telescope, and that's going to be usually a lot better than what you get for another telescope that's on the ground, right?
There we go.
So it's much easier to make measurements of these small angles if your telescope is above that blurring effect of the Earth's atmosphere. And people often wonder, what does that really mean? Well, here's an analogy for you. Imagine what it would be like if you're laying at the bottom of a swimming pool with no water in it. And of course, people are perched on the edge and they're looking at you saying, why are you laying at the bottom of a swimming pool with no water in it, right? And you look up at them and let's say you have 20/20 vision and you see the features of their face or something. And then if that same swimming pool was filled with water and you're still laying at the bottom of the swimming pool and somebody's looking down at you saying, why are you laying at the bottom of the swimming pool with water in it? And when you look up at them, their face is going to be a lot blurry looking.
Right.
Because you have to look through the water, you see. And that's kind of
That's a good way of putting it,
yeah,
describing it. Yeah.
That's a good analogy for the difference of looking through the atmosphere versus having our telescopes in space.
And because of the waves on the surface, even you get that shifting, which is what causes a star to twinkle.
yeah, the scintillation effect.
I'm gonna have to remember that one. That's really good.
So
I'm
to
gonna
get
in my class.
Yeah.
yeah, there you go. Now, to get good measurements, of course, parallax and the position of stars in their motion, the proper motion, you should have your space telescope in space.
Right.
And in fact, this is not the first generation spacecraft, the Gaia mission that you see here. This is actually like the second one. The first one was the Hipparchus mission.
Hipparchus. Yep.
And I believe that was launched in the 1990s by the European Space Agency. And this is a better spacecraft, more sensitive, can measure more accurately the position of stars. And you can see some of the things that it's done. Now that it's over, right, the mission is finished, it's made 3 trillion observations, rounded off. Okay. 2 billion stars and other objects it has observed. So whatever's in the field of view, right? And that would include
Right.
galaxies, but concentrating on stars. And you can see the numbers there as well. So it's operated for almost about 11 years, essentially. And you see publications so far that use Gaia data, about 13,000. So you wonder, are you getting your money's worth, right? And the answer is
And
definitely
142 terabytes of data compressed.
yes. Yeah, compressed.
Holy cow.
So all the data has not been released yet. The last one was data release 3, and I think the final one will be data release 5. But data release 4, which will be released at some point, it contains 5.5 years of observations. That's 500 terabytes of data.
Half a petabyte.
Yeah. So what you can buy now easily for $400, at least in the US, 22 to 24 terabyte hard drives, whether you get them on sale or not. So imagine how many you'd need to get 500 terabytes, how much that would cost you.
Yeah.
So yeah, it's a lot of money.
I'll take a small piece of that. Thank you.
Yeah.
I remember the last data release. I believe it was when you were teaching us the second astronomy course, the 500 level one. Astrophysics course, actually.
Right.
Yeah. So that was 2019.
Yeah. So they don't release them that often. This is public. I'm sure people who are on the project doing the grunge work get access to the data immediately.
Right.
But it's the general public, right? They fine tune the catalogs, make sure everything's good as possible in terms of no mistakes that they made in their computer codes, bugs, all that kind of stuff. So it's tested.
This is something that I'll point out too. What he's talking about, all of this data is generally going to be made at some point available to the public. You can go request and download this data and see for yourself.
Yeah, the data, and same as NASA, all the NASA data is also available at some point online.
Mm-hmm.
And that's because the stuff is paid by taxpayers.
Right. So the scientists get the first look at it so that they can do their job. But then everybody gets a crack at it.
And that goes with observatories too on the ground. So you go to an observatory, you have usually 6 to 12 months where the data is yours, and then it gets released to the public. So if you're lazy or you're busy doing other work and you don't get a chance to analyze it, someone else might scoop you.
You
right?
get scooped.
And that's not good because you want to be able to publish, right?
Right.
Publication is everything. You get the credit of any type of new observations or new discovery if you publish first.
Right.
Even if you go to a meeting like the American Astronomical Society meeting last week and say, hey, I discovered this. And they're like, great. If you don't publish first before everyone else, you don't get the credit.
And to be honest, if you talk about it at a conference, you can now endanger yourself of being scooped because the publication is what really counts.
Well, you got to make sure the publication has just been submitted or ready to go. before you talk at a
That's
conference.
the trick. Yeah.
Yeah. So you got to have that plan ahead of time.
Yeah. So
Now Lachman, I don't know if you've been paying attention a little bit of some of the observations coming from the JWST, and this is observations of what they're calling red dots. Have you seen any of that?
Yeah, I saw that one. I haven't had the chance to look at that one. It's on my list. So, yeah.
So these are objects that have extreme red colors, and they're through spectroscopy, which is what we use to measure distances to extragalactic objects.
Mm-hmm.
These are all at high redshift, which means that they are very far, billions and billions and billions. I sound like Carl Sagan here, light years away.
Except Carl Sagan never said that.
I know that was urban legend. That's probably Johnny Carson started that rumor.
Right.
Anyways, if you look at the panel there's 6 different objects, and there's Z equals some number. So the top left corner is 4.75, then the one over to the right, 8.92 on the top row, and so on. So that's the redshift. And the larger that number, the further away these objects are. And there's an easy conversion you can make based on what you assume the cosmological parameters are. You can directly relate that Z number to a distance in, let's say, light years, for example. And people were wondering what these objects were. So since they're really red, the JWST is an infrared telescope.
Right.
So it's easier to pick them up or to notice them than it would be with like the Hubble Space Telescope that uses optical band passes, right, even out into the ultraviolet. Although there was some infrared observations done with Hubble as well. So this is kind of like a new class of objects. Very red and small in size. They're not like huge extended objects, so hence the name red dots, right?
Right.
And what they're trying to figure out is whether or not this phenomena is tied into the presence of supermassive black holes that sit at the center of these objects. So these are galaxy-like objects.
Right.
And it's the feeding of these supermassive black holes that ultimately produces, emission that comes from the material surrounding the black hole itself.
Yeah, it's not coming from the black hole.
That's
it's
right.
the material around it.
Outside of the event horizon,
Right.
as we would say.
Always got to make that clear.
Yeah, in the accretion disk itself. So from the vicinity of the black hole is where the light comes from. And the thing is, some of these objects are extremely far away, which means that, a telescope, as we always like to say, is like a time machine.
Right. So they're very early on in the universe.
Yeah, that's right. So they're very old. And the thing is, if they're very old, that means that they formed not that long after the universe itself. So as far as we can tell today, the universe is 13.8 billion years old. So I always joke and say if you have a DeLorean and you get it up to 88 miles an hour, don't put in the time machine that you want to go back more than 13.8 billion years into the past, because where would you come out? The universe didn't exist.
Still might be interesting to find out.
Do that experiment, Robert, and let me know what you find.
Sure.
But
sure
remember,
thing.
before you tell me, publish it.
Oh, right.
Now, so if these supermassive black holes are responsible for the activity that we see with these red dots, and if we find these red dots very far away, which means we're seeing them way back in time to very earliest moments of the beginning of the universe, how do you form those supermassive black holes over a relatively short period of time?
Well, that's the question all the way around, isn't it? I mean, how do you form them at all, much less in this early days of the universe? I want to answer that question all the way around.
But if the universe, Lachman, now was 28 billion years old, as Gupta from the University of Ottawa has suggested, then there's lots of time to form these objects.
Right.
But that goes against all the other observations that we have that shows the universe is not that old, that the universe is less than 14 billion years old. That's
Right.
the problem here.
So
the idea is, how do you form these supermassive black holes rapidly? That's the issue. That's what you need to work on. And theorists, of course, are working on that. There's a lot of people interested in this specific topic nowadays. So
my own field of interest, planet formation, there's a similar type of issue, though. Planets clearly have to form very quickly because stars blow away the debris disks, the gas and dust that's around them within 100 million years or so. So you can't take a billion years to form a planet. You've got to do it now.
So, Lachman, when you teach, do you find a lot of people interested in astronomy?
Yeah, I do. We do have a couple of observatories around us, and that helps. So most people from a very young age, they get to go visit the Apache Point Observatory.
Oh, yeah. Okay.
Sorry, not James Webb. The Sloan Digital Sky Survey is at. So Sunspot that's the solar telescope. That's the most famous one. And the road that's leading up to it, it has a scale model of the solar system, as in like they put a name tag. This is where Uranus would be. This is where Saturn would be. And then eventually the end would be the solar telescope is at where the sun would be. So
nice.
That is nice. I like that.
Yeah.
That's
and
cool.
It's a relatively small town, just like Grand Forks. You drive 10 miles in either direction, it's dark skies. So people tend to have a really decent interest in astronomy. And like I said, the Astronomy League at the Space History Museum, that was formed because there's so many astrophotographers around here.
Right.
You have about 50, 60 members as part of our group.
Wow. So do you physically take students on tours to these places?
Space History Museum, yes, we do have star parties. It used to be every month, but due to weather conditions, now we're moving it into a quarterly system. So rain or shine, we're going to have a star party. If it rains, we use the theater and then bring everybody inside and do a show.
Okay.
Yeah, so I try to take my students up there. Obviously, they get extra credit.
Okay. Yeah.
You got to bribe them.
Yeah. So how many times have you been to Apache Point?
I went there a couple of times. One time I actually got the full detailed tour. It was very interesting to see the Sloan Digital Sky Survey, and then there are plates, with the holes drilled in to take the spectroscopy. So it was very neat.
So did you get to see the robot that places the fibers in the fiber optic cables in the holes?
From what I was told, well, no, I didn't get to see it, but I don't think they're using that anymore. At least they're trying to step away from it to go to a different system.
Okay, because I know when it first came out and they started doing the spectroscopy, they actually had people plug the fiber optics cables in the various holes by hand.
Yeah, and I think it's made in somewhere in Seattle, and then it was FedEx to this location, so you can plug in the fiber optics cable.
Yeah, I know the University of Washington is a big supporter of Sloan, so they probably was done there, Seattle area for that.
And a little bit about that, folks, is if you can feed the light of the object you're interested in directly onto the end of a fiber optic cable, you can reduce the amount of data reduction you have to do of playing with the data to clean it up, because you're just looking at that one object now. And so that's what they were doing is.
Yeah, the only problem is that to position those fibers, they base that on imaging data. So they take images of a certain small patch of the sky, know where the galaxies are, the objects of interest. Then they essentially drill holes at where the center of the galaxy would be in the field of view, place the fiber optic cable at each of these holes, and then some would be on the sky, of course, right?
Right.
But then you're only getting the spectra of the very center of the galaxies.
Right.
You're not getting the spectra of outside the center, so it's biased in that sense, right?
Right.
And that, yeah. So
because the center of the galaxy is a different population of stars.
Well, it can
wings.
be, and the other thing that we find at the center are supermassive black holes once again, right? So these so-called active galactic nuclei type galaxies, and so you're taking the spectrum of essentially of the central region,
right?
Not necessarily of this normal stellar population out in the outskirts of the galaxy. So there are a lot of these things that you have to take into consideration when you're analyzing data taken from those type of instruments.
Right. And these are all things you consider when you're writing up your conclusions and
now,
which data sets you want to look at.
Luckily, you mentioned about amateur astronomers. So one of the big things that's come out in the last, I guess, Dean Smith here at UND, he purchased one of these.
Back when they started.
But the Sea Star, is that the name of it?
Yes, C-Star S50. I actually purchased one myself. Oh, actually, I convinced the campus to buy one for me.
but it's not just yours, it's for everybody, right?
It is like, it's mine. No, there's no astronomy professor here other than me.
But you did engrave your name on the side of the tube.
No, I didn't do that. We have a couple of astronomers that work closely with us. They are either working for the Apache Point Observatory or they're retired. I got to learn about C-Star through one of them. And then I talked to my division head, and then he was willing to buy it. And it's been awesome. I got it just before the last total solar eclipse. And even in city lights, I don't go into any dark sites or anything, just from the comfort of my backyard. Actually, I've been doing some interesting things. And I haven't even scratched the surface of this. There's other folks who actually do way better than I do with this little telescope. I think I have some pictures to share.
Yeah, that'd be great. Now, I know there's two different types now. Recently, they put out a C-Star S30, and the original one was an S50. So this is an S50 that you have?
Yes, I have the S50, and I have someone coming in tomorrow because he needs help with getting it set up. That's S30, so I'll get my hands on S30 tomorrow.
Oh, nice.
Nice.
And I know they hook up to your smartphone.
Yep.
Yes.
You can control them that way. So maybe talk a little bit about what these are. So these are essentially electronic telescopes.
Right.
Yeah, smart telescopes. Basically, take out the whole headache of setting your telescope, pole aligning it, finding your objects. None of that's there. You just press buttons and that's it. Just do the thing.
And it's great in an urban area because if you want to see something faint, the problem always is when people start off as amateur astronomers and buy a telescope, they get frustrated rapidly because they can't point it at the object of interest.
Right.
Yeah.
And if you can't see what you're pointing at through like a finder telescope because you're in bright skies, then they give up after a while. But these type of telescopes, you tell it where to point at the coordinates of the object you want to look at, and bang, there you go.
Yep.
sometimes you use the traditional setup, you find it, if you don't have tracking on, and then you say, hey, come here, look at this is cool, and it's gone. It's not there.
I wouldn't know anything about that, would we?
Yeah, so for those people who don't know or are listening to this podcast, so when you point at an object with a telescope, that object's constantly moving because of the rotation of the Earth. Unless you're pointing it right at the pole, like the
right at Polaris or something.
and even that moves a little bit because it's not quite on the exact spot, right? But other than that, every object in the sky is going to move with time. So you compensate for that by moving the telescope.
Yep.
And usually it's automated, so the clock drive, as we would say in the old days, the machinery, knows how to compensate for the Earth's rotation to track that object, so you can look at it for a long period of time and take a long exposure image of it with a camera and so on and so forth. Yeah. So, Lachman, do you want to share some of the images that you've taken with this telescope?
Let's see.
And I heard the price has come down, so I think initially they're on the order of $500, and somebody told me that they thought that they were down to around $350 or so now.
Oh, wow.
S50.
I think the smaller one is...
or maybe it's maybe the S30 is the $350 one now.
I checked, I think this morning it's still $550.
Okay.
Oh, well. So let's get your pictures up.
All right, there you go.
Well, I'm still not seeing them. Oh, there we go. Now we're sharing the screen.
There we are.
So if you want technical detail, I put in details as well. So this is what it looks like. It's big with the stand and everything. You can actually expand these tripods just to make it a little taller. And then you take it, place it. Sometimes you'll have to adjust the north just a little bit. It's an automatic calibration. All you got to do is just rotate the telescope until it completes the circle. And that's it. It's a telescope. It has a focuser and also a camera controller, everything in one place. The camera is, I forgot the brand. I think it's a Sony something. So this is the sensor that's in the camera, this IMX462. I don't know much about it. The controller is an ASI Air. I'm pretty sure that's an acronym, but I forgot what it stands for. It's a very famous controller that amateur astronomers use in their regular traditional telescope setups. It's an apochromatic, so it's lens, basically it's adjusted so that you don't get chromatic aberration, meaning different colors don't get focused at different wavelengths, different focal points, and then blur the image. That's one of the biggest problems with refractors or a telescope that use lenses, but they correct it so that all the colors will get focused at one point, making your image appear much cleaner. It's a pretty decent resolution, and the mount is an altitude azimuth mount. So if you want some technical details, that's just some basic stuff I found. And obviously it comes with the solar filter. So if you want to look at the sun, you just strap the filter on. It just basically fits into a little hole. Just ask it to find the sun. And it finds the sun. And also same with the moon. You don't need the filter, obviously. It does have its automatic light filter on. You can switch it on and off depending on how faint or bright your city lights are, and also which object you're looking at. My house is covered by, on one side there's city lights, and on the other side my neighbor has a floodlight. Then I'm battling some trees too, so I can only see like a little patch of the sky.
But the telescope itself is so small, you could easily like put it in a backpack and go somewhere with it, right?
Exactly. Sorry, go ahead.
I was gonna say, what's the power source? Like if you were to take it somewhere on a hike, what does it run off?
It's run on a battery. You just have to charge it. Once you charge it, it's good for about 5-6 hours, depending on the temperature. Yeah.
Okay, nice.
And because it's an alt-az, you're not taking hour-long images anyway because your field will rotate, but that's another topic.
Yeah, I'll show you some of that in some of the pictures I've taken. And then for like image stacking, we don't have to do the traditional, put it on iRAF or SOI image or anything. It actually does it for you.
Okay.
If you want to look at like a nebula or something like, so before that, this is the solar eclipse. So I got this like I said, maybe week before the total solar eclipse. And I sent it with someone to Dallas, which was in the path of totality. And the first set of images that you see that was taken in Dallas in path of totality, and then the second one is what we saw here in Alamogordo. So we got about 80% coverage.
Right.
And
Right.
both of these are taken from two separate sea stars.
Nice.
Okay, cool.
Yeah. Yeah. So,
That was back on April the 8th, 2024.
2024. Yeah.
Yeah.
Cool.
and then
Oh.
I've been playing with it just to figure out how faint of things can we look at it, and like how long my exposure times have to be. Obviously, I started with the Orion Nebula, 15-minute exposure, and now I didn't do any of the stacking. So what it does is every 10 seconds, it just expose the camera for 10 seconds, take the image, expose, take the image, and then it will stack it for you if you want to continue on the same image. And if I happen to observe, let's say, M42 or the Orion Nebula today and then tomorrow, on the app itself, I can ask it to combine those data. That's why you don't see the date down here. Normally, it tells you what object it is, the date, location, everything.
Okay.
Yeah, and then here's what Robert was talking about earlier because of the rotation. The field is changing, so you lose some data on the top and the bottom. And it doesn't like it very much when it's close to your zenith point. It's like, don't do it. So it has to be about 80. Yeah.
Yeah, and the other thing, so the thing is, if you took data, let's say, in multiple nights, and one night had worse seeing, so the images are a little blurry than other nights, is there a way to reject that data? And
Yes. So I know some folks, I'm being lazy, quite honestly. I'm using everything built in, like it's intended to. But if you want to do, way more better things, that you can actually take that raw image yourself. Then you can run it through your starless software, so get the stars out because I'm only focusing in the nebula, or you can run it through a denoiser, take out the noises, just like what we do with our regular FITS image, then combine it in your own software. And the image actually looks much prettier. So if you want to get rid of some of the images, you can do it then.
Okay.
nice.
Nice.
Yeah.
I mean, this is good work. I can see in the M78 and NGC 3628 that what you're talking about, you have some very good light pollution.
Yes.
That's why it starts looking a little yellow in the block around the object. But yeah, it's still doing a really good job.
For someone who wants to get interested in astronomy or astrophotography and then scared to start dealing with the regular telescope setup, I think this is an excellent.
Yeah.
Yeah, for sure. I mean, if you take like a standard, even a Dobsonian type telescope, how do you take a long exposures, you run into a problem where you don't have the machinery to compensate for the Earth's rotation.
Right.
So you end up having to buy, let's say, another type of telescope that can be very expensive if you want a large size, aperture size. And then you got to buy the camera and the equipment to go with it. It's a lot of work.
Right.
And a lot of people get frustrated and go away from the hobby because of that.
It'll take you a lot more than $500. So this is a good deal.
On that point, this is a bargain.
This is a bargain. Yeah.
And there's few more, obviously.
Oh, nice.
Okay.
And then this one, the one in the middle, actually was taken at a relatively dark spot. We are scoping out a location for a southwestern star party that's hopefully happened towards the end of this year. And right now we are scoping out locations to see if we can find a relatively dark site. And this is one of the sites actually we tested out. So the Andromeda galaxy, you can only see the middle, not the outskirts.
Well,
and it's only 4-minute exposure. And I've seen an exposure that's about an hour long. It's very detailed. You can see the trails, the arms up here.
I was about to say you can still see some of the not rings, the arms, but not much. Yeah,
you
it's
see
mainly
some
the
dust
center.
patches. But I see you got the Sombrero galaxy on the far left, M104.
Yep.
That's very nice. And then on the far right, we have the Whirlpool galaxy.
Cool.
Yeah. And these are just, 30-minute exposures. And they're not the brightest, but they're also not the faintest.
Yeah.
And you can see the quality of the stars, like in this one versus this one. They're, I don't know how to say it. It's not as bulky as you see in here. It might be the exposure and collected more lights, but
it's the full width half max, right?
I was about to say it's probably they still look really round, so I'm betting it's seeing the air quality that day.
Yeah, if it was tracking issues, they'd be smeared out like a
They'd be
oval
football
shape or something. Yeah.
And if you ask it to auto stack, it actually discard those images. Let's say you took, I don't know, you on to about 2 minutes of exposure time, and the next 10 second that comes in has trails. It actually discard it for you.
Nice.
And
Auto
go on to the
rejection.
next
Yeah.
step.
Oh, nice. I know people use like the webcams, and now they're upgraded to like they call them planetary cameras,
Yeah.
where you can take very short exposure, let's say of Jupiter, and the seeing varies. When you look at Jupiter through the eyepiece, you just don't glance at it and you're, oh, that was nice, I'll walk away. You actually look at it for a while because the seeing changes all the time.
So it looks like it's rippling.
Yeah, well, every once in a while you get this all of a sudden really sharp view of it, then it goes away blurry again, then really sharp view.
Right.
And so if you're taking multiple exposures, short exposures with a planetary camera, you can actually reject all of those blurry ones and just keep the ones that had really sharp view and stack them together, and you can get some really high resolution views.
Yeah.
I know a gentleman who's actually using his C-Star to do planetary photography. And it'll be interesting. He just brought it up in the last meeting, so it'll be interesting to see what he has to share.
Nice.
Yeah, for sure. Now, the one that was taken of the Andromeda Galaxy, you said that was taken from a dark location?
Yes, relatively dark location, about 30 minutes away from the city. It's much like the night sky that we see at the Kitt Peak Observatory.
Okay.
Okay.
Yeah. Nice.
Yeah.
It's a good shot.
Cool.
Yeah, and then in honor of our galaxy clusters research, I try to look at the galaxy group, so Leo triplet. It's relatively close by, so it's fairly bright.
Yeah.
And this is also taken from my backyard, just a 32-minute exposure on a single night. Yeah.
Again,
That's
very nice. Very
I try
nice.
to go for like the center of the Coma cluster, Coma Berenices.
Yeah.
Yeah.
See if you can what you get out of that. That'd be cool.
Problem is, it needs to fit into that little window I have open, between the trees and the neighbor's
Yeah, well, just envision that's the slit of the telescope observer of the dome, right? That you got to look through. You just say you can't move the dome.
Yes.
Yeah. It's too bad that the comet Atlas that just went by the sun that wasn't visible.
Yeah.
For us, it really can't see. It's really close to the sun. Where you are, can you see it, Lakma?
So we had actually planned last Wednesday to look at it. It was so unfortunate. We actually had the astronomer Alex Hale from the Hale Bob coming.
Yeah.
Everywhere else in the sky is blue skies, just around the sun.
No.
Frustrating. And it's so close to the sun, you got to have clear skies. And, in the southwest, right, where the sun is this time of the year. So, that's unfortunate.
That was very unfortunate.
Yeah.
I actually, there's another unfortunate thing that happened. I went to the Arches National Park.
Right.
So that's Utah. And someone told me about Moab, Utah. She said it's one of the most prettiest townships she has ever been to in terms of astrophotography. And when my wife said, let's go to Arches National Park, I look up the location. I'm like, oh, wait a minute, it's in Moab. So I prepared everything. I had my C-Star, everything ready to go. I forgot to put the C-Star in the car.
Oh, no.
It is. So if you ever been to the National Park, you drive up a mountain a little bit, then you take a couple of turns. Once you take like the second or the third turn, then the city lights disappear. It's just pitch black.
That was an excuse to buy a new one.
I tried to see if they have any company that I can rent one from, but unfortunately they're not operational during the winter time. So
Okay. Well, at least you didn't forget your wallet.
Yeah.
You wouldn't get far, right? Take a gas, you'd be done.
Yeah.
Oh, well. Well, I guess, the hour flew by already, Robert.
Yep.
So, Lakma, thank you very much for joining us.
yeah, thank you for the meeting.
Yeah, and so if you're interested in learning more about what Lakma does, consider going to New Mexico State University.
Yep. Or join us here at the University of North Dakota.
Yeah, so
Either
always
place, great.
Yeah, for sure. Now, our next podcast will be next Tuesday, January the 28th. Now, at the end of every podcast, we always leave you with a quote. Lakma, I'm going to give you a chance to guess. Who do you think this quote is from?
Which one?
The one I'm going to read off here in a few seconds.
Okay.
Can you think of someone famous who you think that I selected to read for a quote from this person? Who do you think this person is? And it's related to you. Now, the person's not directly related to you, but it has to do, you'll get the connection. It's connected with your background.
want to say Martin Luther King. Is it?
Nope.
No.
No. Another guess? You get one more guess and that's it. Then we got to go. Where are you from, Lakma? Where are you from?
From Sri Lanka.
So what do you think most famous white person from Sri Lanka? Or
Oh,
not? Yeah. There you go. There you go. This quote is
Lordy.
from Arthur C. Clarke. So here's the quote. 2 possibilities exist. Either we are alone in the universe or we are not. Both are equally terrifying.
Yep.
Don't forget to give us a thumbs up. Subscribe if you haven't already. And thank you for watching. We'll see you next time. Thank you, Lakma.
Thank you, Logmall. Goodbye, everybody.